Thank you for the introduction. So my name is Roxane Mamberti, and today we'll talk about the non-temperature fabrication of a resistive memory on flexible substrate. So to contextualize my work, we all know that since the middle of the 21st century, there is an explosion of electronic devices markets. So that lead to the necessity of storage medium for flexible electronic. So actually, the leader market for resistive memory, non-volatile memory is flash-type memories because it has many advantages as a memory, like high and stable performance. But the material that we need to fabricate the flash NAND is silicon, and it's not adapted for flexible application. So research focus on emergent devices, alternative solution like resistive random access memory, because they have simple structure that allows them to have a wide range of application like flexible application. So in our work, we work on a CBRAM memory, which is a resistive electrical-chemical memory. We have a simple structure made with metal electrolyte metal. So their simple structure makes them compatible with printed process. So the working principle is easy. At the initial stage, they're high resistive. That you just need to apply a voltage between the two metal electrodes that creates a filament by the displacement of ion of active electrode towards the counter inert counter electrode. So when the metallic filament is created, the memory became low resistive, so you do a set operation. And if you want to reset the memory and she became high resistive, you have to just destruct the metallic filament by applying a reverse bias voltage on the metallic electrode. So in literature, you can find several materials to fabricate this memory. And the key material of our memory is electrolyte layer. Sorry. And in our work, we focus on oxide for this layer. And more precisely, we focus on Mesoporous silica. Why we chose this material? It's because the Mesoporous silica is compatible with CMOS application and flexible substrate. Memory which use silica as the electrolyte layer show attractive memory performance like high runoff ratio, good endurance, and low power consumption. And the porosity improves the ionic conductivity. And in literature, there are few printed oxide memories. So the aim of our research is to develop fully pretend Mesoporous oxide CBRAM. And in our work, actually, we use a heterogeneous manufacturing process to fabricate our device. So the platinum electrode is made with spattering. The Mesoporous silica is fabricated with subjet process and coated with deep coating. And the silver electrode is printed by inkjet printing. And the final of our work is to have a full printed CBRAM on flexible substrate. So we work on Mesoporous silica seed film, and I don't have the time to present the sol gel technique in details, but we have to create, first of all, a precursor solution that will lead the parameter of our layer, Mesoporous silica layer, like porosity, pore diameter, and the structure. Then we coated the layer by deep coating. And actually, the big issue of sol gel technique for flexible application is that when we want to remove the surfactant template to liberate porosity, you have to annealing to heat the layer at 400 degrees. It's too hot for more of the flexible substrates. So we work to propose an experimental process based on literature at low temperature. So we propose a first step of drying the layer at 120 degrees. And then to remove the surfactant template and liberate the porosity, we use a UV ozone treatment at 3 hours, during 3 hours. So we want to validate our experimental process. So for that, we made with the same solution Mesoporous silica layer treated with a conventional process and with a low temperature process. And we characterize them with isoporosimetry. And with the variation of optical constant, when you file and unfile the pore with humidity, you can establish the porosity of the layer and the pore diameter. So if we compare the both layer, we see that we have the same porosity in the two layers around the 23–25%, and the pore diameter is around 2.5 and 3 nanometers for both process. So our process validates to obtain the same layer. So after validated our low temperature process, we fabricate with the process that I introduced before, memory, and we choose a cross design, and then we measure the electrical characteristic of our device. So the first step is to test the endurances of our memories. So we do set and reset operation during 1000 cycles. So for memory fabricated on glass substrates, we can show that we are high on-off ratio. So here's the high resistive state, so the off state, and the low resistive state, so the on state. And we have a high ratio which is equal to 10⁴. And with good stability, we don't have a lot of dispersion points. And we can also show that we have good endurances because we don't have the decrease of the HRA states, which means that it be the end of the lifetime of the device. Then we do the same thing with the memory fabricated on PET substrates. And we have the same on-off ratios that we have on glass substrates, but we can see more dispersed points for the high resistive states and low resistive states. But we don't have a visual decrease of the high resistive states, so we can establish that we have good endurances over the 1000 cycles. So we validate also the memory on flexible substrates. Then we focus on the current voltage curve during this 1000 cycles. So we can see that for memory on glass substrate, we have typical high curve of CBRAM with well-designed sets and reset operation. We can also show filament nucleation and the destruction of the filament during the operation. And if we focus on the voltage range, we don't show any degradation during the operating voltage. And for memory on PET substrate, we also have typical high curve for CBRAM, but we can notice that we have higher reset currents needed for this memory. But we don't show any degradation for the operating voltage during the 1000 cycle. Then we just focus on statistical charts for operating voltage, and we compare with our previous results that we had last year when we fabricate a memory with conventional annealing process for sol gel. So the previous result was made on glasses. We compare with the low temperature on glasses and memory fabricated with low temperature process on PET. So for the three memory devices, we can see that we are low operating voltage. The one on glasses has the same result, similar results with the device made with conventional process. But for the PET, for the memory on PET, we can see that we are lower set compared to the device on glasses. So to discuss the results, we can see that for memory on glass substrate, we have good performances for memory application, and we find the same results as last year with conventional process. But for memory on PET substrate, we have reliability issue that could be explained by two things. One, the PET substrate is hydrophobic, so we have difficulty to have a good adhesion of the silica layer on the substrate that create cracks and change the layer characteristics. And also we have Joule effect during the measurement due to our electrode design and the current that we need to make our memory works. We use a 1 milliampere to make our CBRAM works, and so the modified layer and lead to measurement error. So to conclude my presentation, we fabricate CBRAM with heterogeneous process. We also validated a low temperature process to fabricate the Mesoporous silica film. And so CBRAM on glasses show good memory performance, but for the device on PET substrate, we have some reliability issue. So the perspective for our work is to improve the silica adhesion on flexible substrates And finally, print the platinum electrode to have full protein devices. Thank you for your attention.